In the previous lecture, I discussed Bohr's model of the hydrogen atom. According to the Bohr model and equation, we can find the energies of the hydrogen orbitals. If an electron absorbs energy, the electron can transition to a higher energy orbital, or energy level. The absorbed energy must be equal to the difference in the energy levels. On the other hand, if an electron transitions from a higher energy orbital to a lower energy orbital, it will emit the energy in the form of a photon. Again, the photon emitted will be equal to the difference in the energy of the energy levels. Bohr's model gives a basis for better understanding atomic structure, but carries some flaws. In this lecture, let's discuss the successes and flaws of the Bohr model of the hydrogen atom. I'll start with the flaws. Bohr assumed that the electron orbits around the nucleus, but there are two major flaws with this hypothesis. First, according to classical mechanics, a negatively charged particle, like an electron, orbiting around a positively charged nucleus, would emit energy as it is attracted to the nucleus and thus accelerates towards the nucleus. Obviously, this doesn't happen. Otherwise, atoms wouldn't exist. The second problem with this model is that the emitted energy, or frequency of light, for example, would match the frequency of the orbit. Think about it. If the electron is spiraling towards the nucleus, then all orbits would be possible. Thus, all frequencies would be emitted. A continuous spectrum would be observed. Again, this does not match the observed atomic spectrum or line spectrum of hydrogen, where only specific frequencies are observed. It is very important to note that Bohr proposed his model in 1913, only 13 years after Planck's work on blackbody radiation, and 8 years after Einstein's work on the photoelectric effect. You can find both of my lectures on these topics on this channel. Quantum mechanics at this point was only a curiosity and not fully accepted. Both Planck and Einstein used quantum assumptions to explain what classical mechanics did not. Similarly, Bohr implemented very important quantum mechanical assumptions to propose a model of the hydrogen atom to help explain the hydrogen line spectrum that classical mechanics could not. Now, let's look at the successes of the Bohr model and begin with Bohr orbits. The nucleus is much larger than the electron. Thus, we can assume the electron is fixed and the electron orbits around the nucleus. The force holding the electron in orbit is described by Coulomb's law, where E is the charge on the electron, the constant epsilon is the permittivity of free space, and r is the radius of the orbit. The 4 pi epsilon term is present due to the use of SI units. The Coulombic force is balanced by the centripetal force, or centrifugal force, which is a force that makes the particle follow a curved path, where m is the mass of the electron and v is its velocity. R is the radius. I'll set these equal to each other and we can see that one r term cancels. Now, let's solve for the radius. I'll multiply both sides by r over mv squared. Here's the equation for the radius of the orbit. Let's set this equation aside and we'll return to it in a moment. So far, I'm using classical mechanics to describe the electron's orbit. However, classical mechanics predicts this electron will spiral into the nucleus, emitting all its energy. Here is one of Bohr's great non-classical quantum assumptions. He proposed an existence of stationary electron orbits. Bohr assumed the electron does orbit around the nucleus, but in fixed circular orbits. So long as the electron occupies an orbit, it will neither emit nor absorb energy. Bohr also assumed that the orbits must be quantized. Angular momentum is equal to mv 2 pi r, where m is the mass of the electron and v is the velocity. This mv term is also called momentum. R is the radius, and 2 pi r is the circumference of a circle. Since Bohr assumed the angular momentum is quantized, the angular momentum must be equal to nh, where n is a whole number integer and h is Planck's constant. Thus, we can set these equal to each other and this time solve for velocity. I'll divide both sides by mass times 2 pi r, and this gives the equation for the velocity. Now, let's return to the Coulombic and centrifugal relationship and substitute the velocity term, which is squared in the radius equation. I'll square the velocity term and rearrange to move the mass 2 pi r terms to the numerator. The integer 4 cancels, 1 pi term cancels, and 1 mass term cancels. Now let's rearrange to get the radius by itself. I'll take the inverse of both sides and multiply both sides by r squared. Finally, here is the full equation for the Bohr radius. R equals epsilon n squared times h squared over e squared m times pi. N equals 1 would be called the ground state, and also called the first Bohr radius. Epsilon is the permittivity of free space constant. H is Planck's constant. E is the charge of an electron. And m is the mass of the electron. Pi is also in the denominator. This gives a first Bohr radius of 5.29 times 10 raised to the negative 11 meters, or 52.9 picometers. This remarkably agrees with experiments on the observed size of the hydrogen atom. Successive integers in place of the n term would give the Bohr orbitals further from the nucleus. Now, let's discuss the energies of orbitals, or energy levels. Again, Bohr starts with classical mechanics. The total energy of the electron is the sum of its kinetic energy and potential energy. The kinetic energy is 1/2 mv squared. And the potential energy comes from Coulomb's law and the centrifugal force, which we saw earlier. The nucleus electron attraction lowers the energy of the electron. The negative sign indicates the electron is lower in energy relative to a free electron. Let's go back to the Coulombic centrifugal force relationship. Recall, one radius term cancels. Notice the mv squared term remains. It appears to be the same as the potential energy term, but with the opposite sign. And the mv squared term can be substituted into the kinetic energy term in the total energy equation. I'll multiply the kinetic energy term by 1/2. And I'll change the 1/4 term to 2/8, so I can have a common denominator. Now I'll simply sum the terms. Notice there is a radius term in the denominator, which is the Bohr radius that we solved earlier. Let's substitute this term into the equation. The energy is equal to negative mass times the charge of the electron raised to the 4th power, divided by 8 times epsilon squared times Planck's constant squared. These are all constants and equal to the Rydberg constant, shown here in terms of joules. This is quite a remarkable achievement by Bohr, to derive the Rydberg constant by using classical mechanics along with imposing some quantum assumptions. Notice the Rydberg constant is multiplied by 1 over n squared, where, again, n is a whole number integer starting with 1. Each successive integer gives the energy of that orbital. The difference in energy of orbitals can then be solved using this equation. Again, Bohr derives the equation proposed for the differences in lines in the hydrogen atomic emission spectrum. Let's sum up. The Bohr circular orbital model is not accepted today. The electron does not orbit around the nucleus like planets orbiting around the sun. However, by using classical mechanics and imposing some quantum limitations, Bohr solved what is now called the Bohr radius of the hydrogen atom, which matches the radius found from experiments. Second, Bohr was able to solve the orbital energies. And third, he derived the Rydberg constant. Thus, the era of quantum mechanics begins. Thank you for watching. You can find my other videos on quantum mechanics and the history of quantum mechanics in this playlist.